Poles and zeros is the title of this lecture. This is the last topic that we're going to talk about in the introduction to transfer functions. However, we're going to revisit transfer functions in a couple chapters, so don't feel like they're going away anytime soon. We've got a good idea of the definition of a transfer function, how to derive a transfer function from a differential equation, how to derive a transfer function from a state space model. And now we're going to talk a little bit about a couple of objects that are defined in terms of the transfer function, called poles and zeros. And then some system properties and relationships among representations that we've talked about so far. So that's on the docket for today. So the first definition that we'll encounter is of poles. So let a system have transfer function h. Its poles are defined to be values of s for which the magnitude of h approaches infinity. So the magnitude of h is used because h is a complex valued function, right? So that's important. And also we want to take the absolute value as well. So it sort of takes care of both of those aspects. So if it goes to infinity, if h goes to negative infinity or positive infinity, then we have a pole there. So that's a pretty easy definition. It's not super complicated, right? But there are a lot of things we can do with this, and that's what we'll unpack. So a transfer function written as a ratio, which most of our transfer functions that we've looked at so far, actually every transfer function we've looked at so far, we've eventually written as a ratio, right, of two polynomials in S. Right? We did that last couple lectures. So if it's written as a ratio, it has poles wherever the denominator is 0. That is, S for which we're going to use this denominator operator function here. So just den means the denominator of h of s equals 0. So nothing magical there. Whenever the denominator of a fraction is 0, the fraction approaches infinity, right? Blows up. Divide by 0. I know. This is really complicated stuff. So divide by smaller and smaller numbers until you're convinced of this. Okay, so the denominator of h is 0 means, there's a pole there, so we could solve for values of s for which this occurs. And since the denominator could be written as a polynomial in s, you gotta find, you're getting ahead of us, but you're getting there. It's good, you're connecting it. But yes, so you can find the roots of a polynomial to find the poles, which is what we'll do. Okay, zeros. Another definition. Let a system have transfer function h. Its zeros are values of s for which the magnitude of h goes to 0. I know. It's weird. But that's what a 0 is. A transfer function written as a ratio has zeros wherever, the numerator is 0. That is s for which the numerator of h is equal to 0. So this is So we care about poles and zeros. Poles are actually more important in some respect for the reasons that we'll unpack throughout the rest of the lecture. So one thing that I'm ignoring here is what happens if the denominator and the numerator go to 0 at the same time. And so you have to, I'm skirting that a little bit. This is actually these definitions are typically what are taken to be the definitions of poles and zeros. However, you get into this concept called pole-zero cancellation, which we'll talk about another time. And we'll call those poles and zeros also, which is to say we kind of take this to be the definition of a pole, or of a pole, and this to be the definition of a zero, instead of it just being a consequence of them. This is like sort of terminological subtlety, and we'll deal more with that later. This is sort of a common issue in the terminology, but I wanted to use the definitions that are standard definitions and not try to fix it, because you guys would be caught up in the sort of mess of trying to straighten out a sort of bad terminology. So I'll just keep it to the standard thing, and there's a little bit of weirdness that we have to talk about later in terms of our definitions of poles and zeros, but we'll deal with that when we get to it. For the most part, the denominator of h equals 0 gives you the poles, or the numerator of h equals 0 gives you the zeros. And we'll just use that pretty much universally. So given a transfer function h with n poles pi, notice I use n there. Interesting, reusing a symbol. Doesn't mean anything necessarily. What did n stand for before? Number of derivatives. Also, the size of the state vector, which is also the system order, right? So it's like several things. It's a little, I wonder why he's reusing that. Might come into your mind right now. Okay. And Greek n, new, zeros, zj. We can write for some constant k the following identity, which is that the transfer function can be written as some constant times this ratio. So the ratio is of, we're going to use the capital pi for product. I'm going to make it a little higher so it's easier to see. The product of the expression we will write from j equals 1 to nu of s minus zj divided by the product of the terms from I equal 1 to n of s minus pi. So what is this? So remember, so just in case, we don't see this, we see the sum a lot more often than we see the product, right? But this is just the same as the summation notation, but we're using product of each term instead of the sum of each term. So the product of s minus the zeros in the numerator divided by the product of s minus the poles in the denominator. So what we're saying is that if s is equal to a 0, so say like j is equal to 2, okay? So we have z2 there, some 0, z2. And then s was equal to z2. Then z2 minus z2 would be what? 0. And we're going to take the product of 0 and a bunch of other terms, which is going to give us 0. I know. And that's going to make the numerator 0, which is going to make the transfer function 0, which means we have a 0. Yeah. All right. So that's what the numerator is. And the denominator is the same, but for poles, right? So whenever the denominator goes to 0 is whenever s is equal to one of the poles. Now, this is interesting that we can write the transfer function, which we've said is a complete system representation, right, for a system. So just like the differential equation or a state space model, you can write it all in terms of its zeros and its poles within a factor k. So that means that zeros and poles are pretty important, right? They're pretty key. Okay. So for a single transfer function, we can define a single input, single output system's dynamic model within a constant. So if there's one input and one output, it can be described with an input-output differential equation, right? Just a single input-output differential equation. And a single transfer function, which can be described in terms of its poles and zeros within a constant. So that's pretty cool. Okay. Recall that for multiple input, multiple output state space models, the denominator of every transfer function, remember we find the matrix transfer function, and that's what we did at the end of last class, right? We found a transfer function from each input to each output. But that the denominator of every transfer function is the corresponding system's characteristic equation, right? Which is to say the roots of which dominate the system's response and are equal to its eigenvalues. It is now time to observe a crucial identity, which is a system's poles equal its eigenvalues equal its characteristic equation roots. Okay, this is really key. So poles we've defined in terms of the transfer function h, right? Eigenvalues we've defined in terms of a system state space model, right? So I'll just write like state space. Specifically, we used the A matrix to find the eigenvalues. And the characteristic equation roots come from the input-output differential equation, right? Just the scalar input-output differential equation. So these three different system representations yield identical quantities that are related very intimately. They're all key quantities, right? Poles we just learned about. Eigenvalues we learned about in the last chapter. They were pretty important. And then the characteristic equation roots were how we went about solving for the system solution, right? Especially the free response, but also the forced response as well. So those poles, those eigenvalues, those roots of the characteristic equation dominate the response, and they're all equivalent. So if you are in one representation and you find the eigenvalues, say you're in state space representation, you find the eigenvalues, you know, oh, those are the same as the roots of the characteristic equation in the differential equation representation. If I was to transform this into that representation, I would just see these are the roots of the characteristic equation. Similarly, you would see that the transfer function poles are equal to those same eigenvalues. So, pretty cool. Therefore, everything we know about a system's eigenvalues and characteristic equation roots is true for a system's poles. So we can just like copy and paste all of our knowledge from those onto our new representation. This includes that they characterize a system's response, especially its free response, and stability, right? So we will explore this a little bit now. So pole zero plots and stability. So we'll comment on both of these. The complex valued poles and zeros dominate system behavior via their values and value relationships. We're going to really expand on the values in this section, but value relationships we might get into more towards the end of this course. You can get this thing called pole zero cancellation that I'm sort of foreshadowing a little bit here, but we'll talk more about that later on. It's a more advanced topic. Often we construct a pole zero plot, a plot in the complex plane of a system's poles and zeros, such that such as that of figure 3.1. So let's look at figure 3.1. So the complex plane, remember, has as the horizontal axis the real part of a complex number, and on the vertical axis, the imaginary part. So since our poles and zeros are all complex numbers, we can represent them here. If they were all real numbers, we could represent them all on a real number line, right? Just like this, like 7, 2, etc. So we can do that with a complex number in the complex plane. And we're going to do that because their sort of geometrical positions and relationships are meaningful. And we can kind of get a feel for the system based on looking at its pole zero plot. Okay? So this system that I'm drawing a pole zero plot for has 9 poles, and a pole we represent with an X. Okay, so important. Poles. And zeros we represent an O with an O, a circle, zeros. So this system has, count the poles, 1, 2, 3, 4, 5, 6, 7, 8, 9 poles. Okay? And it has 4 zeros. What is the order of this system? 9. And why is it 9? Number of poles is the number of eigenvalues, is the number of roots of the characteristic equation, is the order of the system, is the number of state variables that represent the system, right? So 9, it's a 9th order system, which is pretty big. I'm not going to give you guys a lot of 9th order systems. So the number of zeros actually, it's interesting, has no impact on the order of the system, right? It actually has to do with how the input of the system comes in, how it enters. So let's look a little bit deeper at this. So we can represent these. Notice a couple things. First of all, the poles and zeros always show up in complex conjugate pairs. So if there is one that's, say, like -9 and +5 or whatever this is. So this would be like representing, say, -9 plus J5, if this length was 5. Then there's a pole that has to match up with that at -5 or -9 minus J5. Okay? They always show up that way. And this is a consequence of the fact that we have this polynomial representation in the numerator and the denominator. If you have real coefficients, if you have a complex pole or zero, it always shows up with a conjugate pair. So it always shows up as a conjugate pair. So there's symmetry about the real axis. It's an important thing to remember. Yeah?
Where's the -9 and 5 coming from?
So I just made those up, but just say that this is in the, I said this is approximately -9 back here, so I just made up the scale. But -9 and then +5. I'm just saying that this could be what is being represented there. Yeah.
Sorry, so you were saying that if it's off of the real line, that it's always going to be in a pair?
That's right. So it's always going to be in a symmetric pair about the real axis. So anytime you go up, or you find one that's positive anything in the imaginary part, it's going to have a symmetric one about the real axis. So wherever you see one that wanders up off the real axis, it's going to come as a pair. All of these that do that come as pairs. So this one is paired up with, I shouldn't probably circle it, but this one's paired up with this one. So you can also get zeros and poles that show up as just real numbers, right? And you can also get those that show up as just pure imaginary numbers too. So these ones here have no real parts. They're just pure imaginary numbers. And we've seen all of these. Remember when when we started the semester, we were talking about first and second order system responses, right? Second order systems have roots of the characteristic equation that can be complex, right? That was one of the cases. So that's if it has a negative real part and it has a non-zero imaginary part, you have a complex root, and that gave you damped oscillations, right? And we're going to talk a little bit more about the interpretations that come from that. So when we're thinking about these poles, we're thinking about roots of the characteristic equation, right? And these are the cases that arose back when we were looking at second order systems. Part of why every system shows up as being a bunch of contributions of first and second order systems is that you have a bunch of complex conjugate pairs of poles and a bunch of and then real poles. So the real poles contribute like a first order system. The complex conjugate pairs contribute like a second order system. So, okay, that's some stuff with the pole zero plot. So from our identification of poles and eigenvalues and roots of the characteristic equation, we can recognize that each pole contributes an exponential response that oscillates if it is complex, right? Remember when we did that for roots of the characteristic equation for a second order system, we got an oscillation if there was an imaginary part. Okay. There are 3 stability contributions possible for each pole pi. So if the real part of the pole is less than 0, a stable decaying contribution happens. So that means if the real part's negative, which is to say anything in the left half plane, right? All this stuff. So all these poles contribute they have stable contributions to the system. If we have a pole that has 0 real part, it's marginally stable and neither decaying nor growing contribution. So if you're along this line, on this imaginary axis here, so these 3 poles contribute a marginal stability to the system. They aren't unstable, their contribution doesn't grow, but it doesn't decay either, it just stays. Okay? And then the last case is when the real part is greater than 0, which is to say an unstable or growing contribution. So anything in the right half plane contributes that. So this guy right here, this guy right here, and this guy right here contribute that. This is only the poles that matter. Having a 0 in the right half plane, like we do here, it has its own contribution that it gives the system, but it's not instability. These systems are notoriously difficult to control. They're called, and I do call it here, minimum phase. And it's a topic that you talk about in a more advanced dynamic systems or controls course. Minimum phase systems do funny things. For instance, the step response of a minimum phase system, just as a little aside, say you had a system that was minimum phase and you put in a step input. Instead of responding like you would think maybe second order system would respond to a step input, a minimum phase system instead starts off and it goes down first, and then it comes up. So they do weird things. They're harder to control. They're harder to deal with. So if a 0 shows up in the right half plane, that kind of stuff can arise, but kind of just like beyond the scope of this course, the non-minimum phase system. Oh, and I didn't put the non in there. Non-minimum phase. Non-minimum phase. So beyond what we're going to talk about in this course, besides just that, just understanding that if a 0 shows up over there, it doesn't mean that the system's unstable. It just means that it's non-minimum phase and harder to control. Okay, so just to just know that much about it, and that's all you need. Okay, and then let's see. Explored graphically in Figure 3.2. So what I've done here is I've shown a bunch of different pole locations, and I've drawn little free response plots that correspond to the contribution that pole would contribute to a system. So if you've got a complex conjugate pair and you start off with some initial condition, you're going to see this thing return to equilibrium, but it's going to oscillate, right? This oscillation occurs because it's got some non-zero imaginary part. This is just straight up what we talked about with second order system responses, free responses. You're going to have this overshoot and oscillation thing that happens when you look at the free response if it's a complex conjugate pair of roots of your characteristic equation, or similarly poles. Okay, so we've got that contribution there. Let's look at what a pole on the real axis contributes. Notice that its real part is negative. It's in the left half plane. So it's stable, right? As this one was stable, it goes back to equilibrium. This also returns to equilibrium, but it does so just as an exponential decay. All right? And it's a little bit hard to tell, but the decay is a little bit slower of a decay than this one was. And it turns out that this is a trend. The further you move to the left out here, the faster the system will decay, whether it oscillates or not. Remember, the oscillation has an exponential sort of envelope on it, right? So it's hard to see that, but an exponential envelope on the oscillation. So the faster decays happen way out here, and the slower decays happen closer and closer to the imaginary axis. Let's look at another complex conjugate pair that's closer to the imaginary axis. This one also oscillates, but notice that it has a slower envelope. It's decaying slower than the complex pair that's out here. So this is a slower decay. Still has oscillation, slower decay. Okay. If you go all the way to the imaginary axis and you have a pair of imaginary poles, these two, then that corresponds to an oscillation that neither grows nor decays, right? So if you let this thing go at some initial condition, it's just going to continue to oscillate. The one that always freaks people out is the one at the origin, and I didn't draw it because it freaks people out. But I will draw it. I will draw it here. I'll draw a little box for you guys. So that one, what it does is say, it's hard to represent because you can't see where 0 is, but I'll draw in a line that's 0 first. And then I'll change colors for the effect here. So what happens is that if you start off at an initial condition, it will stay at that initial condition. It won't decay, it won't grow, it'll just stay at a flat line that's non-zero. It's not going to go back to equilibrium. It's not going to go off to infinity. It's not going to oscillate either because it doesn't have any imaginary part. It's just flat. It just hangs out there. Wherever you put it initially, it stays. It's like I'm good. Yeah.
So since it's at 0, it's not going to stay at 0? It's going to be slightly above it, 30%?
So yeah, this is the initial condition right here. So this is our say like y of 0. And usually when you start off with some initial condition like this one, y of 0, if it's stable, it's going to decay back down to 0, right? But since you have a pole at the origin, then your system, when you started off at some initial condition, it just stays at that initial condition. And it doesn't change at all, which is kind of weird, but it is a total real thing that happens a lot. So the classic example of this would be if you've got, I'll change back to black. Is it if you've got a ball that's like rolling around on a frictionless surface, and you started off with some initial velocity to the right, and it doesn't have any friction. So like v0 equals 5 meters per second. It's just gonna keep going, right? It's not gonna slow down, it's not gonna speed up, it's just gonna keep going. So that's the sort of the idea with this system that the zero pole gives you this often it's associated with this translation that continues. Okay. Now I want to go over to the right half plane because we're expecting this to be the unstable part, right? So let's do that and start off with an initial condition, and this is a complex pair of poles, and we get an oscillation again, but this oscillation grows, okay? So every time it comes back up, it grows, and this has an envelope, an exponential envelope that's growing instead of decaying. So when our pole pair has a real part that's positive, we have this unstable behavior, okay? Similarly, if you have a real pole that doesn't have any imaginary part, start off at some initial condition, and it'll just go off to infinity. And of course, as you increase, as you go further and further to the right, you can notice that this is faster growth that happens further to the right. So obviously we don't want systems to end up there after we're done designing them, but they might start that way, and we need to use control to make them stable. So we have to understand how they work a little bit, although this is typically seen as being, anytime you're over here, it's a mistake. You don't want that. Or that's how your system started. You don't want to design a system that's unstable. At the end of the day, you want to bring all these poles back to the left-hand side. That's what we use control to do. A lot of times we think about control of dynamic systems is moving these poles to positions that we want to get a certain response that we want. We'll talk more about that later. So this positioning of poles guiding your idea of how the system is going to respond is something that just continues on. So throughout dynamic system analysis and design, once we get to control, especially, thinking about the placement of the poles and what that contribution will be to the system's response is totally key. Now, let's see, there we go. Of course, we must not forget that a system's stability is spoiled with a single unstable pole. So these contributions, like if these were all poles for one system, okay, this system would be unstable, right? Because there are 3 unstable contributions to it. But all you need is one unstable contribution, and your system as a whole is unstable. Okay? So we would need all of the poles to be in the left half plane if we wanted the system to be stable. If we had just one on the imaginary axis and the rest of them in the left half plane, it would be a marginally stable system. It's like one of these weakest link things, right? So the stability of a system is the stability of its weakest pole, okay? Its least stable pole. So, and then if you have any poles, even just one pole, even if you've got 500 poles, if one of them is in the right half plane, your system's unstable. Okay? All right. It can be shown that complex poles and zeros always arise as conjugate pairs like we discussed. And as a consequence, the pole-zero plot is always symmetric about the real axis. So if you've drawn yourself a pole-zero plot and it isn't symmetric about the real axis, good thing to go back and check what happened. It's probably wrong. Well, it's definitely wrong. Okay, second-order systems. I wanted to specifically call these out because we've talked about these before, but we didn't talk about them in terms of transfer functions and in terms of poles and zeros, right? So we want to think about what that means for a second-order system. Recall from the first chapter that second-order response is characterized by a damping ratio zeta and natural frequency omega n. These parameters have clear, complex plane geometric interpretations as shown in figure 3.3. And this is over here. So, that line's a little light. Can you guys see that there is a gray line that comes in? It's like an arc. Yeah, it's pretty faint, but okay. So this is the same thing that we did before, but we're specifically thinking about second-order systems, and we know, of course, that every time we see a complex pole, there must be one that's symmetric and down here, right? But I didn't draw those in because it would have taken up twice as much space. And we already know that, so we don't need to draw them. Okay? So what I want to look at is, if we look in this quadrant and we think about the location of these poles, we already kind of have an idea of, you know, if the pole is further to the left, it's going to decay faster. If it's further to the right, it's going to decay slower. And then once you get to the axis, it's going to not decay at all. The imaginary axis is not going to decay at all. But we want to think about what that, how that is related to our two parameters for second-order systems, the damping ratio and the natural frequency, so zeta and omega n. And there are geometric understandings of how they affect a system in the complex plane as well, and that's what this plot's all about. So we have, let's start with this guy right here. So we have a pole, a real pole, and in fact, this real pole, if it's a second-order system, it turns out, and this is something that we wouldn't think about yet, it would show up as a pair symmetric about this zeta equals 1 point, but that's not too important to know yet. It's just an accident that you'll see will occur. Later we'll understand why. So this happens you've got this pole here on the real axis. We know that that's just going to be, it's a real pole. The system has to be symmetric about the vertical axis. If it's got one real pole, it's got to have two real poles, right? Because you can't have one that's out here. So if it's a second order system, if one's on the real axis, the other one's got to be. And it turns out that it's over here for this case. Now, two real poles is just going to be an exponential decay, right? You're going to have two different exponential rates, an exponential decay. And we called this overdamped before, right? So zeta greater than 1. So if you have real poles for a second order system, it's an overdamped system. Okay. Remember we had this thing called critically damped, where zeta equaled 1. So when zeta equals 1, we actually have a double root, which we typically draw with like double x. Same spot. Double root right there as zeta equals 1, which is, remember, the sort of threshold between when a system is going to oscillate and it's not going to oscillate. And zeta decreases from 1 as we go along this constant arc right here. So it goes from zeta equals 1 down to zeta equals 0. So if you started here, when zeta equals 0, you'd be moving to the left on this arc. You'd be moving counterclockwise. And the arrow points this way in terms of increasing zeta. So as zeta increases, we have responses that have less and less oscillation until zeta equals 1, right? So we follow this arc down. Zeta equals 0. We just barely get to this point, and if we continue up, zeta is equal to 0 along the imaginary axis here, and we have an oscillation that never decays, right? So no damping. As you go along this arc, zeta is increasing until it gets to 1, at which point it's completely damped. So think about it from starting here. Oscillation, less oscillation, less oscillation, no oscillation. Okay? Now, this arc that we're following is an arc of the covenant now. It's a constant natural frequency arc. Okay? So a constant natural frequency arc is a circle about the origin. It turns out geometrically, the natural frequency is the radial component here. So if you start at the origin and you drew a line to there, the length of that is the natural frequency. So notice that the natural frequency did not change with all of these. Well, I guess it changed a little bit with this one because it went up a little bit. But with these two, natural frequency is the same. And our omega n is there. And then our zeta actually is the angle. It can be interpreted from the angle. So it's the arc cosine of zeta, which means that for one zeta, everything along an arc, or everything along a ray starting at the origin and going outward is constant zeta. So if I go, see if I can do this. Draw a ray. This would be constant zeta. Along an arc like this would be constant omega n, constant natural frequency. Okay? So you could think of this as like a polar coordinate grid where you have these arcs of constant natural frequency, and along rays, you have rays of constant damping. Okay? So that's sort of the geometric interpretation of the natural frequency and damping ratio of a second order system. We're going to use this a lot when we start controlling systems. We're going to want to say, oh, I want a zeta of 0.2 for my system. So I have to put my pole here. So we'll talk more about that later, but it'll help us.